Hello, everyone. This is Bill Bittner. Today is Monday, March 23rd, 2020. With us today, we have our part two of a three-parter on SSI and LGR, and Jacob Gagnon is going to take us through LGR and relocation domains. So I'll turn it over to Jacob at this time.
All right. Thank you, Bill. Welcome, everybody, again. This is another installment, as Bill said, of our series on SSI, and I remain your host from last week, Jacob Gagnon. I'll tell you, I'm excited about this one because I've been lucky enough to work in the LGR and SSI area from time to time with my role here at IBM. I've been working with ZVM in the last 5 years. While I didn't necessarily write any of the code for any of this to work, it was a little bit before my time. I do get to support it and kind of see some of the inner workings of it. While it's complex from the inside standpoint, it's a pretty cool technology. And so hopefully we got an informative session for you today. So we'll start off today with just a recap of kind of what happened last week with SSI, and then we'll really take a moment to break down LGR into a bit more detail. And that'll serve as kind of the front half of this hour. And then we'll spend the back half of the hour talking about a very important construct of LGR, and that is the idea of relocation domains. What are they? What are they used for? And so once we've kind of laid the groundwork for what the relocation domain construct is, we'll describe some common uses of those domains. And as I said, that'll be the back half of the presentation to round it out. So SSI, if you were here last week, then you should be very familiar with SSI. If you weren't, then I'll point you to that recording so that you can become more familiar with just the basics of how it works. But just a quick summary here to refresh our brain. Again, all it is really a clustering solution for ZVM that allows us to connect up to 4 ZVM instances together into a single SSI cluster. And so this has a lot of benefits, right? Primarily being the ease of management in terms of managing multiple VM systems, right? It's easier to manage one cluster than it is to manage 4 individual systems. And it enables the all-important topic that we're here to learn more about today, which is live guest relocation. Now, LGR, our brief synopsis of that from last week was that it's that vehicle for allowing us to move a live running Linux workload from one VM system to another without having to take an outage to the actual Linux guest itself. Now, one thing you'll remember me saying from last week is that relocation is not something that's automated by CP. It's a decision that you as an end user have to make. But I do want to clarify a point on that, just to make sure we kind of frame it right. Just because CP doesn't automate this task doesn't mean that it can't be automated at all. Right, we have a lot of hooks into this LGR stuff that we'll kind of see today that allows us to kind of build automation. This picture we saw last week, some new colors just to keep you on your toes, but the picture is the same, the details are the same, right? This is kind of that picture we put in our minds as a frame of reference when we're talking about this stuff. And we'll have a lot of other graphics to kind of show the LGR process, but this is our SSI, right? We've got our shared volumes for all the shared data that we need to make our SSI work, all the CTCs that form our ISFC-based communication for the cluster, our common network fabric, and things of that nature. So nothing new here. Now, the meat and potatoes of this presentation really start off with live guest relocation. And so I want to take some time to really understand the stages of that process, right? And what actually happens when we move a live guest, a live Linux guest, from one system to another. And so it all starts when we issue the VM relocate move command. This is the command that sets everything in motion. Now, step 1 of a live guest relocation is something that we call eligibility checking. Now, what do I mean by that? Perhaps to kind of best explain this, it's reasonable to take a step back for a second, right? And talk about a different flavor of VM relocate, which is VM relocate test. This is kind of a variant of VM relocate that will actually issue these eligibility checks and go no further. We do this to see what we need to satisfy for relocation. We don't actually initiate the relocation itself. So test is often suggested is really the first step to LGR so that we can run it without having risk of things going wrong or getting too far before we know it's going to be bad, right? So what kind of things do we check when we do this eligibility checking? There's going to be a lot more of this throughout the presentation. I'm going to sprinkle a lot of the talk of eligibility checking throughout the hour. But just to give you some ideas of some of the things we check, we need to check things like our guests' virtual processor configurations, all CP or all IFL. They need to be. In other words, we can't run in a mixed virtual configuration. Is there a matching configuration that's on the destination member that we want to go to? In other words, are there identical disks and shared segments to access? If not, then we don't have an identical configuration, and that's something that we need. Is our guest running disconnected? So a lot of different things that we'll check to make sure that when the relocation happens, it's going to be safe and that we're going to get there and be just fine. Another thing that plays into this is one that I'll talk about a lot in some later charts, which is, and I kind of hinted at this a little bit last week, this idea that we can have a guest that has a higher capability set in terms of the hardware and software facilities and features that he's using than what would be available on our destination member, right? And that's something that we'll call a virtual architecture level. And that's something that we need to make sure we have everything available to us on the destination that we have now, so that we're not taking away any capability. So that's something that we'll kind of digest a lot more through this hour as well. The point is, we can start off and do this non-disruptive eligibility check. We can see what step one of this process is by doing a VM relocate test before we actually do a move itself. But let's say that we are going to actually go through and do a relocation. We issue VM relocate move, and we've passed our initial eligibility checks, right? Step two of the process then is to create a skeleton on our destination member, right? Now, the skeleton is exactly that. It's a framework that we're going to instantiate on the destination member so that when it comes time to move our guest, the meat and potatoes of our guest, we actually have a structure to put that on. So it includes all of the crucial control blocks that define our guest, the DAT structures that define our guest's memory. It will reserve the resources that the guest is going to need on the destination member. Really, at the end of the day, the way I kind of like to think about that skeleton is that it's a series of baskets that are going to catch all that necessary information from the guest when we start to throw it over from the source side to the destination side during a relocation. Now, once we have a skeleton user on our destination side, we can start to move the guest's memory. And remember, we do this as the guest continues to run. Now, this is one of those processes and one of those bits of ZVM that I think is really a bit of magic. Now, maybe it's because I'm not necessarily a memory guy. I'm in the processor support area. And so memory management in general is pretty jaw-dropping to me. But the fact that we're able to move a guest's memory while he's still using it is pretty impressive. And so I'll spend a few more charts to walk through the high level of how that process works. So to kind of unlift the veil behind the magic a little bit, in order to move our guest memory without the guest knowing it, we need to make a series of passes where each pass is going to push more of the guest memory from the source side DAT structures to the destination side DAT structures, right? So pass one is going to move all of the guest memory to the destination side. That's pretty easy, right? But remember that our guest is not stopped. So he's still referencing and changing pages. So this is a process that we need to walk through iteratively. So on subsequent passes through our guest DAT structures, we're going to try to find any of the pages that have changed since our last pass through. That way, we're kind of keeping our destination side skeleton in step with our running guest from a memory standpoint, at least to the best of our ability. Now, how many times we have to go through this process and how many passes it's going to take is going to be a healthy dosage of it depends. Our ultimate goal here is to meet a series of thresholds at which the number of changed pages for a single pass are low enough that our final memory move isn't going to take too long. So we want this to be true because the final pass through, the final move of memory that we actually do while the guest is temporarily quiesced. Now, I know that kind of breaks the whole idea of live guest relocation, but the truth of the matter is that for a short period of time, we do need to quiesce the guest just to do our final memory move and move the guest over. But this should be relatively quick, and to the guest, he really doesn't take an outage. So we want this to happen, but it's not a simple matter of programming. Sometimes our Linux guests can make things difficult. Sometimes they're just referencing memory really, really frequently and fast. And so If it seems to CP that our iterations aren't really being effective, in other words, the guest is changing pages faster than we can keep up and move them, then we'll actually cut this process short. We'll quiesce the guest right then and there, and we'll move whatever is left to move. Now, like I said, we want that quiesce time on the guest to be as short as possible so that it doesn't be observable to the guest. And that time that it takes is something that we in CP estimate. And so if it looks like, if we project that that's going to be too long of a process, then we can actually abandon the relocation if necessary. Now, what deems too long is the threshold you can actually define for yourself, right? So you have some control over that because every workload and every environment is different. What you are willing to get away with is different. So that's something you can define yourself. So now we are at step 4 of our live guest relocation process. And this is where we actually quiesce the guest on our source side. Once we do this, we're not going to allow the guest to be run on the source side anymore, right? And then the next step of our process is going to be split into 3 overlapping threads of execution. Now, these 3 threads execute in parallel, and we do that so that we can even further minimize that quiesce time that our guest observes, right? We have to do 3 distinct operations or sets of operations. And if we can do them together, we don't have to be down for as long. Step 5A is the guest state move thread. It's a very brief thread of execution. Really, all that's involved there is actually moving all the data that defines what our guest was doing when we temporarily quiesced him. So that's things like the contents of the guest registers, any control blocks that ZVM needs to describe what our guest was doing when we stopped him. We'll move all that over so that when we actually get him running again on the destination member, he can just pick up where he left off and nothing changes. Step 5B is the IO device move stage. This can be a quick process or this could be a long process. It really depends on how many and what type of IO devices the guest has. Essentially, this step gets our IO in order. Now, the most important thing here is that we need to make sure all of the IO on the source side is done before we start running on the destination member. The way I kind of think of it is like when you go to shut down Windows or Mac and you get that message, it says, shutdown can't complete because these following applications are still running. Now, sometimes in that process, the applications will quiesce themselves and shut down and we'll be fine. Or sometimes we have to force quit the applications. And the story is pretty much the same here. We might wait to see if the IO will complete and do it that way. But if that's going to take too long or for certain IO operations, we might just cancel them altogether. Either way, once the IO is no longer active on the source side, we can move the definitions over to the destination member, attach or link them to the skeleton that we created, and then queue up any error messages for the IOs that we did have to cancel. That way we're not losing or missing any IO. We'll be able to see those messages and know that on the destination member, we have to kick those off again and retry them. Now, the third thread of execution, step 5C, sounds way cooler than it probably actually is. Penultimate is just one of those great words in the dictionary. But all this thread really does is move as much of the remaining guest pages as it can while the other 2 threads of execution are running. Now, one question you may have, I certainly had it, was why penultimate, right? Why not just the ultimate memory move? Because, our guest is quiesce. Well, we have to remember here that these 3 threads of execution are running in parallel. So there's nothing to say that during our penultimate memory move thread that maybe our IO move doesn't let another paging IO go through and change what we just moved during step 5C. Since we have no guarantee of that, we can't do that ultimate final memory move. This is just kind of getting most of it, scraping through and getting as much of the remaining data as possible for that final memory move after these 3 threads of execution are done and completed. So back to our graphic, our final pass is when that guest is quiesced. Those 3 executions are doing the final movements of all of the IO and the guest state and as many of the other change pages as possible. So now, after those steps are done, we can have our final memory move because we'll truly be sure that all IO is complete. It's not going to change any more memory. And then we can actually resume the guest on the destination member, right? When we come up on the destination member, we have to make sure to log off the guest on the source side. And then at that point, our relocation would be complete. Now, if for some reason in the middle of this process we fail an eligibility check or other crucial piece that we need for relocation, then we can alternatively log off the skeleton and keep running on the source side. But if all goes well, we are good to go. And this is kind of that process. Now, this is a pretty high level description. We've kind of boiled it down to 7 steps here. But in reality, there's a lot more that goes on behind the scenes that makes this magic run. And we certainly don't have enough time in an hour to reveal all the secrets, but I think this does provide a very good overview of what happens. So to keep going, this is a lot of material we covered last week, so I'm not going to dwell too much on this slide or the next chart either. If you want more information on some of the stuff that's on this chart, you can go listen to the replay from last week. The story of this chart really is a reminder that ZVM does a lot of checking and policing of the state of the SSI cluster, right? Making sure that any transition in the cluster happens smoothly and effectively. We went through a lot of this last week. Same story on this chart. This chart is reminding us of that safe mode state where if we detect there's a problem in the SSI, we'll lock down the features of SSI that would not work without cluster stability. And so relocation is one of those things, right? We will not let you relocate if we find that the state of the SSI is not in a stable state. Okay, so before we get into how this LGR stuff might work out for us, just another couple of quick notes on eligibility checking. Like I mentioned earlier, we'll start off a relocation with an eligibility check, but that's not the only one that we do. Right? We'll actually check multiple times throughout a relocation and really do our best to make sure that when we relocate a guest, it's because it's safe to do so. Now, sometimes we have found with clients that our checks have been maybe overprotective, and that we might flag something that, and often when we flag something, it comes across as an architecture incompatibility. And that's something that our level 2 folks, and then myself and our other LGR guy will look into. And we might determine that, it's flagging this incompatibility, but it's not actually going to cause any problems if we relocate. So for some cases, we might suggest that use a force operation, which essentially pushes through the red tape and the flags that we get with the eligibility checking and goes on with the relocation anyway, right? Now, this is not something that we suggest doing lightly or on a whim. It's not anything I would suggest a client do without, at least talking with IBM first, because we have tools and ways that we can look and make sure that it's safe for a guest to actually move. But it is something that we have done in the past. At this point, let's take some cycles to walk through how LGR might be used for a variety of different situations. And then we'll get into our discussion of relocation domains and how those can help us even further take advantage of LGR. So as you can see here, the good news is VM workload is more and more critical thanks to Linux on Z, right? And all the good work there. But as I'm sure all of you are aware, this means that we don't have a lot of time for taking maintenance or outage windows. Right. So in this case, LGR can be very useful to help minimize the cost of those outages. So let's say, for example, we want to apply some service to member A in our 4-member cluster here. Now, what we can do is divvy up the workload from workload 1 onto each of the other 3 remaining ZVM members, right? Now, why not just completely offload workload 1 onto just one of the other members, right? One thing we need to remember is that with relocation, we have to make sure that we have the resources on our other members to cover that extra workload and that workload that we're moving around and taking on the destination members, right? And so we're relocating in this case to do service on member A, but we want to make sure that that guest is still able to perform, relatively well. So sometimes if we can split up the workload and spread it out across multiple systems, that might help further minimize the impact of taking an outage. But either way, once workload 1 is off of member A, then we would be able to shut down member A and then completely bring it up with new service or whatever we need to apply, and then move our workload back to member A. Right? So that's a common use of LGR for managing planned outages. Not the only use though, right? So let's look at another example. This time, instead of using LGR and SSI to handle service and manage outages, we're going to use it to provide an effective and robust testing grounds that we can use for moving new workloads into production. So I kind of touched on aspects of this scenario last week. We'll dive a little deeper now. In this case, we have two ZVM members that are running production workload. And so they'll have the full access to resources. They're running all the important critical work. And then we have two other members that are pre-production instances. So they're going to have a more limited set of resources, but the advantage is that we can use those members to test new workloads without worrying about messing any of the other workload up or, God forbid, taking an outage or taking one of the production systems down in some way. So let's say here we have some new applications in the pipeline. We've been running them for a little while in pre-production to kind of work out any kinks, right? Once we're happy in these applications have kind of proven their worth, we can roll them into production with LGR. So we would move them onto those production LPARs, and then they would effectively be proven applications, and we could, grab that next new application and throw it in the pre-production pipeline. So we've also seen customers and clients use this for that production environment management as well. Okay, so now we're a little more comfortable with the idea of LGR, and we can take some time to talk about the final key piece of SSI and LGR, and that is this concept of relocation domains. Now, before we try to understand what a relocation domain is, I think it might be best to try and decipher why we might need a construct like a relocation domain in the first place. Right, so let's think of it this way. IBM Z systems are highly flexible and dynamic. Now, one of the things that we talked about is that each system in an SSI cluster is a combination of a hopefully supported hardware and software level, right? And so each member may potentially have a different set of capabilities from that hardware software perspective. And what we want with LGR is a way to be able to move virtual machines around with relocation without having to think about what hardware or software capabilities I have or need to have or duplicate on a given member. If I have to think about all that stuff, then that's going to add to our maintenance costs, and it's really counterproductive then to the value statement of SSI, which says, make my life easier. Don't make me have to manage the world. What I think might be a good idea to do is look at how a similar migration scenario might happen with LGR, but this time from a hardware perspective. The hardware changes often, I think, at least in my mind, better reflect some of the capability differences that can exist within a cluster and for guests of our cluster. So hopefully this will make dissecting the need for relocation domains a bit easier. So let's say that we have a 4-member cluster. Right, we have 2 Z13 KECs, and we're going to have 2 LPARs on each. What we want to do is upgrade this cluster from the Z13 machines to the Z14 hardware. Or I guess for the sake of being modern, you could visualize this as also currently being on Z14 and moving to Z15, right? The process would be the same. What we would do is move the workload off of one of the Z13s. In this case, we'll move members C and D workload to members A and B, respectively. Right? Then with that workload offloaded, we can move out that Z13 and move in the Z14 box. Then we can bring members C and D back, and we can move that workload that we offloaded originally back onto members C and D. Now, at this point, the workload that is running on members C and D could take advantage potentially of the new features that came in with Z14. But in order to do that, they'd have to restart, right, and pick up those changes. If we did that, though, and our guests on member C and D started to use those new capabilities that come in with Z14, we may not necessarily be able to relocate them back to the Z13 members anymore. It's going to all depend on how our relocation domains are defined and what our overall virtual architecture that we're giving to our guests looks like. And so that construct of a virtual architecture level is what we'll talk about next. Now, we could also duplicate this process to move that other Z13 to a Z14, at which point the whole cluster would be at that Z14 capability level. But I'm going to leave that as an exercise to you guys to kind of visualize how that would work out. More importantly, we want to really start deciphering this whole relocation domain thing. So to finally answer what a relocation domain is definitively, right, we can define it as a subset of members in an SSI cluster among which virtual machines can freely relocate. So one of the key aspects of a relocation domain is what we have been calling this virtual architecture level, right? In other words, of the members defined in this domain, what is the maximal common subset of all the members' hardware and software facilities and features? Once I know that maximal subset, I can run my guests at that virtual level and pretty much guarantee that relocations within that domain can happen freely and without risk of breaking that architecture requirement. Now, several of these relocation domains are defined by CP as defaults. So you'll get one domain for free for each individual member. This is something that we in-house at least call the canonical domain, and it defines only that member. So any guests in those member-specific domains will be able to use whatever capability is on that member. We also have a default that we define called the SSI domain, which by contrast has all of the features and facilities that are common to all the members that exist within the cluster. The fun doesn't have to stop there. You can actually create for yourself any number of domains that you want, but they're really only useful in clusters with 3 or more members. If you only have a 1 or 2 member SSI, then you already have all the domains you could possibly define by default. So certainly if you don't have a 3 or more member cluster, don't even think about defining user domains, because if you do, you're just going to probably create some confusion and hassle in the long run. Now, to actually create domains for yourself, we'll go through the commands you can use to do that, but there is a system config statement to do it when you come up, or by command if you want to define a domain on the fly. So let's walk through these domains and what they might look like. And then we'll also go through and define some different domains and why we might define some user domains ourselves. So we're going to have a 4-member cluster here, and each member has a varying level of support. And so in this case, member 1 is going to be on a Z13, so he has the Z13 instruction set, and he's going to be running ZVM 6.4 base code. So anybody defined in this member-specific canonical domain would have access to those features and capabilities from the Z13 and ZVM 6.4. Member 2 is the same, except for member 2 is also going to have this APAR, which I'm going to reveal a little later, is guarded storage, and also has CPACF, right? And so a little more capability from a software perspective than member 1 has. So again, any guest defined to member 2's member-specific domain would have access to those additional features. Member 3 is on the Z14. He gets to have the Z14 instruction set and capability, running ZVM 6.4 and also with guarded storage. And then member 4 has all the goods, the Z14, ZVM 6.4, and our 2 additional features in guarded storage and CPACF. Now, in addition to these member-specific domains, we have our SSI domain, which takes that maximal common subset, which would be the Z13 instruction set and ZVM 6.4. Now, something to remember with the member-specific domains, any guest defined there cannot relocate anywhere because they're defined to that member-specific domain using capabilities that may not be present on other members. But those defined in the SSI domain can relocate freely among any of the members. So now let's look at how we might define some additional relocation domains to kind of help further our cause here. Now, my wife's family loves bears, so I'm going to define some bear-specific relocation domains just for the fun of it. And we're going to start with a domain that we call polar, right? And this is include members 2 and 3. So here, that would mean that we have a Z13 instruction set and ZVM 6.4, but we also get guarded storage. So if we want our guests to be able to use guarded storage, but also be able to relocate off of one member to another, and we could define this domain, and then they could relocate freely between members 2 and 3, use guarded storage, and all would be well. Now let's define another one. This one we're going to call Panda. Again, same exercise. Here we're running the Z13 instruction set. We get guarded storage, and we also get CPACF. So this domain includes all the software features that we can possibly have. And so the only difference between the 2 members is the hardware level, which we have to keep at a Z13 instruction set because of that maximal common architecture requirement, right? So here, a guest could take advantage of both the guarded storage facility and CPACF and still be able to freely relocate between members 2 and members 4. Since we're having loads of fun, we'll do another one, and we'll call this one Grizzly. Again, same exercise. You probably answer what this looks like now, and that would be the Z14 instruction set, ZVM 6.4, and guarded storage, right? So the advantage to this domain is that we'd have that Z14 capability and instruction set. So anything that uses new Z14 instructions to make things a little more efficient, we can take advantage of. And we can still relocate freely between members 3 and 4. If we put that all together, we get a pretty beautiful picture, I think, one that I think Bob Ross would be proud of. For those of you that don't know who Bob Ross is, he was a very soft-spoken, very kind-hearted artist that had a television program here in the States to teach people how to paint. And I think he'd be very proud of this picture. The point here, though, is that we can define domains that give us different capabilities and kind of changes that common subset of features that guests of that domain could use and still be able to relocate for, right? And we'll go through some other uses of user-defined domains at the tail end of this presentation as well. So how do we actually go through then and define the domains? As I mentioned, we do have a command to do it, a CP command, as well as a system config statement. So define reload domain would be the CP command, and then the relocation domain statement would be for the system config. On both of those, you would define the name of the domain that you're defining, and then the members that will be participating as input. Now, something to be careful of is that once you create a domain, it's going to be there for the life of the cluster, right? And there's no way to delete it without completely redoing your cluster, or as you'll find out, clearing the PDR, which effectively resets your SSI. So one of the reasons I mentioned that is because if you're playing around with this and you think, I'm going to be funny and define a cute little relocation domain, just be aware it's going to be there for a while and people will be able to see it. The other thing to note about defining the relocation domains themselves is that this really just defines the playpens which our virtual machines can play in, but it doesn't do anything to actually assign a virtual machine to a specific domain. And so that's something we'll talk about now. At creation time of a virtual machine, we will assign it a domain. And so where it gets defined by default depends on what the user is. For ident users, those multi-config users that we talked about last week, they're going to be assigned to the member-specific canonical domains, and that's something that you cannot change, right? They will always be associated with that domain. But for single config users, our standard users that are running the important workload, they'll by default get assigned to the SSI domain, so that by default you can relocate freely wherever you want to go in the cluster. But you can change that assignment with the cp set VM relocate user command. And if you do a set VM relocate off, then that would mean that this particular user cannot be relocated, is not eligible for relocation, right? And in that case, we'd still assign him to a domain, to the SSI domain, but we would just leave him there, right? He wouldn't be able to actually relocate to any other member. Now in the directory, this is how you might see this as well. So for this particular user, LGR RH56, we turn on VM relocate, which means he is eligible to relocate to anybody that's assigned within the domain of Panda. Right? And if we go back, we'll remember that the Panda domain had that Z13 instruction set, but also had guarded storage and CPACF available. So they'd be able to relocate freely between members 2 and 4. So now that we hopefully understand relocation domains a little bit better, and specifically how those domains help set the virtual architecture level for guests within that domain, it means we're equipped now to discuss what architecture fencing is all about. So because of what we just talked about, there may be members within a domain that have higher capability than the actual virtual architecture level to which they're assigned. What this means is that we need to create a fence for those guests so that they don't see the features that they have but can't use. At the end of the day, what we're basically doing is telling our guests, you know what, you can't live up to the full potential that you have. And we do that by not actually telling them what their full potential is, right? And that's what architecture fencing is, right? Now, maybe that makes us horrible VM parents because we're capping the potential of our little children here. But in our minds, at least, we're doing this for the best, and we do it so that we can have that flexibility of relocation. So what types of things play into the architecture level? Certainly processor facilities are a big one, right? So any instructions that come in with each new processor family is something that plays into it. We also have entire architectures that come in. So things like enhanced DAT or large page, or it could be processor features like crypto cards or the levels of those crypto cards, right? Now, those are examples from a hardware side of things, but ZVM levels also come into play. What do we support from VM? So let's say the hardware supports guest large page. Does every ZVM level in our domain support that for guest use? Quick hint is the answer is no, because we don't support large page. But if we did, that's something that we'd have to consider, right? Are there any new features in ZVM that we care about using, right? I'll tell you a lot of times, when we are assessing new features and functions within CP, we always assess to see what are the relocation concerns, right? Is this something that we have to be concerned about when we do our eligibility checking? Is this something that we need to think about when it comes to that virtual architecture level? And so we have discussions through and through. It's one of those common criteria and considerations we have to make for any new item. So anything that our guests can take advantage is something that we need to assess and possibly fence. So that virtual architecture level sets our stage for relocation eligibility. We'll fence off those big ticket items so that they're not going to be roadblocks to your ability to relocate. But that's not the only consideration that we have to make when checking for eligibility. So a couple more things to know, a lot of which I kind of mentioned up front and gave you that sneak peek. I mentioned that your guests need to have an all IFL or all CP virtual configuration, but also your virtual machine can't have any T-disk, right? Because we won't necessarily have that on the destination side. So we have to make sure that there's no T-disk. We can't have any open spool files. If we have open spool files, that's going to mess with our cross-system spool considerations with relocation. So no open spool files, no XC mode VM. So a lot of different examples of other things that can contribute to relocation eligibility, a lot of which is well documented in our pubs for anything outside of our virtual architecture level requirements. Okay, so look, we live in a very dynamic world, right? And because we can be swapping out hardware and software with relative ease, what that means, and the caveat is that our virtual architecture, and therefore that maximal common subset of features that we can use, can always be changing. Now, as those capabilities are changing and our guests are restarting to pick up those fresh capabilities, our ZVM relocation process has to adapt to be able to handle that. So sometimes we might find that we can upgrade that fence if our overall capability can be upgraded in a domain or cluster, right? But sometimes we might find that we also have to maybe put a guest onto an island of its own if for some reason the overall capability has been downgraded for a cluster, which doesn't happen as often, but is still something that could happen, right? Now, we do a pretty good job of managing that complexity of the outside world. To the end users, things still work relatively well. But we have found times that we're looking at a particular client environment and some of the relocation data that we get, and there's some pretty complicated and unique relocation structures that are formed from these dynamic changes and varying architecture levels and who's assigned to what. And all that complexity is stuff that we have to manage. So let's walk through kind of a final example of how virtual architecture levels play out, again, during one of our common relocation scenarios. So let's say that we start out with a 2-member cluster, and we're going to have a Linux guest on each. Now, when we look at the SSI domain between these 2 members, we're looking at the Z13 instruction set, ZVM 6.4. Now, member 2, in addition to that, is running cpacf and this fictitious APAR that we'll just use for the sake of argument here, VM 99999. Imagine that being that most desirable feature in ZVM that you could even fathom. Now, our Linux guests are assigned to the SSI domain by default, and so they're going to start off with that same virtual architecture level as the SSI domain, the Z13 instruction set, and ZVM 6.4. Now, we're doing our common relocation scenario, applying some service to member 1 to upgrade the overall capability of our cluster. And so we can start by moving Linux guest A off of member 1, and then we can shut down member 1, and then bring in that member with the upgraded support, that fictitious VM APAR. At this point, the SSI domain capability changes. Now the maximal common subset includes that fictitious APAR. So this is a whole new virtual architecture level that comes into play. Now Linux B and Linux A are still on that old level because we haven't restarted those machines, right? Now, of course, in our relocation scenario, we can move this back to member 1. It's now running on a member that has that fictitious support that we couldn't use, but we would have to restart to do so. Now, certainly anybody that came on to the cluster after this point, so if we started a new Linux guest C, then they would get that new support. And for Linux A and B, if we restarted those machines, then we would also pick up that new support, right? Okay, so the general life cycle of relocation domain is this, right? We create our defaults and any user-defined domains, of course, over the life cycle of our cluster. These domains persist even as members are coming online or going offline from a cluster. And because I've used the word persist here, hopefully it's not going to surprise you when I say that information on these relocation domains is kept in the PDR, right? So one thing that we have to consider here is that because we keep domain information in the PDR, if we copy that PDR volume in some way, let's say we're copying it maybe to create or mirror an existing SSI cluster, or maybe we're doing it for DR purposes, we need to consider how that domain information would play out. Sometimes, especially if we're doing a mirrored cluster and we don't want that information, there is a clear PDR option in IPL Farm that we can use, which will clear out that PDR, essentially acts as a hard reset for our SSI. Now, I use clear PDR all the time on my second level test SSI setup because I want every IPL of that test system to be fresh and new. Typically, I test code that's supposed to break SSI or I think will break SSI in some way. So I want to make sure I clear out any of that problem from the last test. And so I'll use clear PDR a lot. You may not, but something to consider there as well. So a couple other ways that we've seen relocation domains used in the field. We've seen some clients that will set up domains specifically for security. And so members of that domain may have things like encrypted paging or some other security feature. We do this, or we've seen this done so that virtual machines can only relocate to members that have that security, right? They can't relocate to somewhere where things are not as secure. We've also seen domains set up for performance reasons. So if we look at the example of SMT, right, there might be some workloads that run better SMT1 versus SMT2 or vice versa, right? So we could set up a domain for each of those, and then guests could freely relocate wherever they run best. And we can prevent accidentally relocating to a member that would have a lower performance. We've even seen relocation domains set up for redundancy, so having even and odd domains where the actual virtual machines are paired for redundancy. So a lot of other uses, and there's probably more out there as well that we have not included that maybe you can dream up of how you might be able to use it in your configurations. All right, so this is the last slide, I promise. I do like to leave you with information on what you can do and look at as things go wrong, or if you just want to look at the status of some of this LGR relocation stuff. So we offer a variety of query commands. The reload domain flavor will show you what domains you have defined and which members belong to which domain. The VM relocate flavor will tell you the domain that a specific virtual machine is in. We're not restricted to just queries here, right? With VM relocate, we get a little bit more. Like I said, we have the test option on VM relocate, which we can use to look at the eligibility and see if we'll be cleared for takeoff before we actually go ahead with the move. We also have a status option on VM relocate, which you can use to see the progress of a given relocation. And if all else fails, we do have a package out there on the downloads page called Reload Down. Now, this is something we don't expect you as an end user to be able to analyze yourselves. So typically what would happen is if something's going wrong, we can't get what we need from a query or VM relocate status, then we'll have you run this reload exec and then send the output to us, right? And then ZVM level 2 guy, as well as myself and our other LGR person, will kind of analyze that information. Basically, it captures all the information we need on what relocation domains are there, what various virtual architectures are at play and in use, what virtual machines are using what architecture, right? So there's a lot there. The thing I would want to note here is that I would highly suggest you run reload down once before you do LGR for the first time, maybe after you've set up your SSI and got the relocation domains as you want them. And then again afterwards, right? Certainly if you have a problem. That way we kind of have an idea of what life was like when you first set things up and when things was good. And then, we can see better what changed. That said, things do change frequently. Our virtual architectures change frequently as you're moving new machines, new support in and out. And so if you have the disk space and you plan on doing relocations often, I might even suggest you keep a few output files periodically saved off so that we can try to best capture that starting point of when things we're good and okay, and we kind of have a timeline to work off of. But that's something that you can rely on as well if you really get stuck. With that, we've reached again the end of what hopefully was an informative session. A reminder that Bill will take the reins next week and wrap up our 3-part series with talk of performance. But thank you all for joining.
Have a good week, everybody, and we'll talk to you next Monday.
Thanks for watching. If you enjoyed this video, don't forget to like and subscribe to see more videos like this one. Have a suggestion for another video topic? Feel free to leave a comment below.